This presentation is based upon an evaluation of unmanned aircraft systems, UAS, as a practical tool for land management and ecological restoration, made for the Geospatial Lab Advanced GIS course Fall of 2020.
This presentation is hosted by Kevin Eng, a graduate student at the University of San Francisco, Masters of Environmental Management program. The development of UAS systems has highlighted deficiencies in our current techniques when monitoring environmental restoration projects. Traditional monitoring techniques, such as boots-on-the-ground surveys, are encumbered by the physical terrain of these environments. For instance, soft substrates and wetlands make human traverse difficult at best and impossible more often than not. In addition, human impacts during these monitoring events may lead to unintended negative effects on the environment. Often, environmental monitoring is costly and time-intensive. Environmental restoration projects suffer from the limited funds, so long-term landscape-level monitoring is often overlooked. Only recently has UAS technology become cost-effective and user-friendly enough to employ in mass scale. This is reflected on the fewer number of primary literature using UAS compared to more traditional monitoring techniques. My research objectives for this study aim to provide evidence to answer the following question. How can UAS technology be employed effectively in ecological restoration and land management? First, I proceeded to understand UAS data collection by collecting aerial imagery using a drone vehicle. This was followed by the processing of individual images through the Pix4D software. Next, I aimed to understand and develop a data analysis method within ArcGIS Pro. Useful data was imported and analyzed to produce a land cover classification. Lastly, I sought to understand the practical implementation of these outputs by calculating statistical data. I chose to focus my study on the Lone Mountain campus at the University of San Francisco. I aimed to employ this test site as a proxy for an ecological restoration site, as permission was not granted in time for the term project. I divided my methods into four main parts: collect data, process and import data, analyze data, and review outputs. Data collection using drone technology. After securing permission, I conducted an aerial survey at the Lone Mountain campus using the Pix4D capture software that allowed me to dial in my study area. Once set, the program autonomously captured aerial data. Post-flight data analysis using Pix4D Mapper. I uploaded hundreds of still photos into the program and ran it overnight. I then reviewed the outputs for accuracy following my knowledge of the study area. Lastly, I determined which data I was going to use. This included the orthomosaic imagery, the digital surface model, and the digital terrain model. Geospatial analysis within ArcGIS Pro. After importing the orthomosaics, DSMs, and DTMs, a model was built to combine a normalized DSM, a DSM minus the DTM, and the orthomosaics. The image classification wizard was then employed on this raster file. Pulling data from the raster. Using the raster statistics tool, I was able to determine the number of pixels per land cover type. This allowed me to calculate the percent cover of each cover type and its area. When using the random forest method in the land cover classification wizard, the results provided a land cover classification map. By reviewing the data pulled from this map, land cover percentages were determined. For instance, buildings made up 41% of our land cover class. In restoration practices, this is important to be able to determine the spread of revegetation efforts. Since we know the raster pixel size, land cover area can be calculated. This is important in environmental monitoring. For example, we can determine the area of infestation of a particular vegetation species. What are the benefits? UAS-derived data is cost-effective and has been shown to deliver useful monitoring data. These terrain models can help determine surface hydrology. Slope and elevation is important for species management and can be modeled over the study area. Using aerial data, real-time spatial relationships can be evaluated. Lastly, data in 3 dimensions can be recorded, providing a more robust data set. Land cover classifications allow us to track landscape level changes over time, provides visual evidence of these changes, and gives estimates of land cover percentage. Where do we go from here? Next steps. Employ this technology over potential restoration areas. Public opinion. Provide empirical evidence to the general public and land managers that this technology is beneficial. Incorporation. Design methodology that employs this technology from the very beginning. Keep moving forward. This technology is evolving quickly, so adapt to change. I would like to thank Dr. David Sa for providing guidance over this project. His insights and motivations were invaluable. In addition, I would like to thank the University of San Francisco for approving my flight over the campus. For other great video presentations from past geospatial work done within the GSAL lab, please visit the link below.